Okay, welcome to this lesson on latent heat, or sometimes it's called specific latent heat. Please date your work here. So we're working through this unit on matter. We've already talked a little bit about internal energy, so we're going to sort of talk a little bit more about that and talk about some calculations we can use with it. We've already covered specific heat capacity in the energy unit, so there is a video available for that one. If you want to go and revise specific heat capacity. So let's jump straight into latent heat. Make sure you dated your work. I will know what is meant by the latent heat of vaporization. I will know what is meant by latent heat of fusion. And I can apply the formula E equals ml appropriately. So, revision. What is the formula for specific heat capacity? Well, if you know it, write it down. I'm just going to reveal it now. E equals mc delta theta. E, should know this already, E is energy, M is mass, C is specific heat capacity. That's measured in joules per kilogram per degree C. And this delta theta, well, delta, as remember, is change in, and theta is the temperature, so change in temperature. You multiply all those three together, and you'll end up with the energy required to raise the temperature of a substance. So, let's look at the first question. An electric heater provides 40,000 joules of energy to a well-insulated metal block, which is initially at 35 degrees C. The metal has a mass of 450 grams and a specific heat capacity of 900 joules per kilogram per degree C. Assuming the block doesn't melt, so it's not going to, what type of internal energy is being added? So we're going to heat a block of metal and it's not going to melt. So its temperature clearly is going to go up. But adding energy to it, its temperature is going to go up. So when it does that, what's going to happen? Well, fundamentally, if you should know by now, what we're looking at is that the more you heat it, the more the particles vibrate. So they vibrate in a solid. The key expression, I suppose, to describe their structure is that the particles or the atoms are vibrating in a fixed structure. And the more we heat them, the more they vibrate. There's no breaking of bonds, which is what is required to increase their, to change substance from a solid to a liquid, or a liquid to a gas, due to a change of state. If they were changing state, then that would be an increase in potential energy. When we're just increasing the temperature of the substance, that is an increase in kinetic energy. That's the kinetic part of internal energy. So, what is the final temperature of the block, assuming all the energy is transferred into the block? Well, let's have a look at doing that one. We can do the calculations here. So have a pause of the video now. Have a go at doing it yourself first. Write in, here's it in a triangle, where in this particular question we're going to calculate delta theta first. So write down the formula. E equals mc delta theta. Rearrange that for delta theta. Have a go. Delta theta equals E over mc. Now we just need to put our numbers in from the previous question. 40,000 was the energy. The mass was 450 grams. Remember, we've got to change that to 0.45. 900. And that gives a solution for, oh, there we go, 98.8. More or less core. So if that's delta theta, and what was theta? Well, the final temperature was going up. The final temperature was going up. So we've gone 35 plus 98, and I just rounded that up to 99 there eventually. So it's 35 plus 99, which gives us 134 degrees C. So please have a look at that if you haven't done that already. Make sure you can understand what we're doing here. So let's just maybe talk a little bit about what we mean by latent heat. Well, when we add energy to a substance, we can heat it up. But we're not heating it up, we're changing its state. So a very common change of state is changing liquids into gases. So how do liquids get changed into gases? Well, that could be called the specific latent heat of vaporization, when we change a liquid into a gas. And the specific the way we measure it is when we talk about changing 1 kilogram, that's our unit mass, and all this happens at the same temperature. Another type of change of state is changing from solids to liquids. And again, so the specific latent heat of fusion, this stage is called fusion, like a fuse that melts in a plug, goes from a solid to a liquid. That's what fusion means, to fuse something. The energy required to change a mass of 1 kilogram or unit mass of the substance from a solid to a liquid at the same temperature. So both of these, latent heat of fusion and latent heat of vaporization, involve changing bonds. In this very simple representation down here, you can sort of see there's a solid with all the particles joined together. Okay, so all the particles can do is vibrate and shake. If you break some of these bonds and you make them into smaller particles, and then maybe there's weaker bonds that come in that don't keep the particles in a fixed structure, they're more liquidy and they can move around, and then eventually if you break all those bonds, which is going to take energy, you'll end up with something a bit more like a gas. So in your own words here, a nice full sentence, just what is the difference between the latent heat of fusion and the latent heat of vaporization? That should be straightforward. Okay, now there is a formula that goes along with latent heat, and it's the same formula for latent heat of fusion or the latent heat of the latent heat of fusion or the latent heat of vaporization. And the formula is E equals ml. Let's put that in a triangle. E equals ml. What does E stand for? Well, the E is the energy, obviously. M is the mass in kilograms. And L is the latent heat. Could be latent heat of fusion or the latent heat of vaporization. We need to look at the question to see the context. Now, we cover up M, we see E over L, and if we cover up L, we see E over M. So there we go, we put those two formulas in. We've done that a few times now, haven't we? So there are 3 different versions of that formula. You always start off with the standard version. If you're going to do any working, explaining, you're going to start off with this version here and then rearrange it. What does it mean? The latent heat refers to the heat released or absorbed as a substance changes state. And remember, that's all going to be happening at the same temperature. So there's no delta theta appearing in this formula. No delta theta. Okay, let's move on and do our first question. Question: 99,600 joules of energy is needed to turn 50 grams of liquid nitrogen into a gas at -196. Okay, so we've got 3 bits of data. One of them is redundant. We don't need the data. Calculate the specific heat of vaporization of nitrogen. Well, the one that's redundant is the temperature, because we know there is no temperature change. This is just telling us what the actual boiling point of nitrogen is. It's not going to affect the value. So it says it's all at 196. It could just say it's at constant temperature. We don't need necessarily to use that in our calculation. So let's write down our formula. It's E equals ml. We've been asked to calculate L, latent heat of vaporization. So L equals E over M. Let's put the numbers in now. There's one thing you need to watch out for. It's 99,600 divided by 0.5 because it told us in grams. Yeah. Do the calculation. And do the calculation. And I've missed out there. I'm going to do my quick fix per kilogram. Oh, and per kilogram, because otherwise they're not in the right units. There we go. So the answer is 199.2 kilojoules per kilogram, or 199,200 joules per kilogram. Let's go on. Right, so for the next ones, have a go at doing these. Please pause the video now. There's no point like just copying down answers or jumping to the end. Have a go. They're all very similar to that first example that we've done. So take a pause, have a go at doing them, and then I'll go through the answers. Okay, Ready to go through them. Calculate the specific latent heat of fusion in. 28,000 joules of energy is supplied to turn 2 kilograms of solid oxygen into liquid at... Oh, I can't actually read that because it's hidden behind there's something that's helping me do the recording. But that's just the temperature over here, so we don't need to know that one. So that's the temperature, that's going to be used. 2 kilograms, 28,000. Okay, E equals ml, so L equals E over M. Let's put the numbers in. 28,000, there's the energy, divided by 2, and the answer comes out at 14,000 joules per kilogram, or 14 kilojoules per kilogram. Fine. That's so easy, isn't it? So if you haven't had a go at the others, please stop and do them now. Have a go at doing them. Get the answer yourself. It makes you feel so much better. 183,600 joules is supplied to turn 3.4 kilograms of solid sulfur into liquid at, so this is the latent heat of fusion again. E equals ml. L equals E over M. Let's put the numbers in. 183,600 divided by 3.4. 54,000 joules per kilogram. 54 kilojoules required to convert every kilogram of solid sulfur into liquid sulfur. And that happens at 115 degrees C. That's its melting point. Now, next two questions just switch to vaporization. So it's still the same formula pretty much, but now we're just doing vaporization. Still going to be E equals ml, but we're looking for the energy required to change from a liquid into a gas. So 335, 200 joules applied, and it turns 400 grams of ethanol into a gas. E equals ml, L equals E over M. 335, 300 divided by 0.4, which is 838 joules per kilogram. I mean, some people do, like sometimes you might see this written instead of this L here. They'll for the vaporization, they'll do a little V here, and for the fusion, they'll do an F. It's not necessary often because the context of the question tells you whether you're doing LV or LF. But if you want to add that, that's fine. Okay, 987,800 joules is supplied to turn 2.2 kilograms of liquid nitrogen into a gas. It's vaporization again. And it happens at minus 253, but we can ignore that. E equals ml. Put the numbers in, and if you want to add that V here, just to show that's a V, there you go, that's fine with me. Okay, I think realistically, you won't be asked anything more complicated than that at GCSE, but let's have a go at doing a few more. I don't think they're going to give you any problems. Again, if you haven't done these yet, please have a go doing them yourself. Please have a go doing yourself, and I'm going to go through them now. How much energy is required to turn 2 kilograms of water at 100 degrees C into steam at 100 degrees C? So there's our constant temperature again, no delta C, so it just becomes E equals ml. This doesn't even need to be rearranged. So E is 2 times, there's the specific heat, the specific latent heat of vaporization, 2 kilograms. There's the vaporization, 452,000, which is 4.2 megajoules. If you haven't got the capitalization right, you did it yourself. You need to get the capitalization right. That's M, capital M. That means a million. Little m means a thousandth. So there's a big difference there. So make sure you get that right, please. How much energy is given out when 500 grams of steam? Now, this is really the same calculation, but just in reverse. Clearly, if you need to add energy to water to make it into steam, well, when steam converts into water, it's going to give up its energy. It's going to give up its energy. So it's still going to be E equals ml, but it's with this, and it's still going to be the latent heat of. We're still going to be using the latent heat of vaporization of water, but it's just in reverse. So it's just, you know, we don't need a negative sign, but we're realizing we're giving out heat now. So E equals ml. Put the numbers in. 0.5226, same as above, and we end up with 1.13 megajoules. If I wanted to, I could go down here. This is LV, if you want to, because it's all vaporization. What mass of oxygen can be boiled if 138,450 of energy is supplied to liquid oxygen at minus 1873 degrees C? The specific latent heat of vaporization of oxygen is 213 kilojoules per kilogram. E equals ml. So M equals E over L. That's our rearranging that for there. Let's put the numbers in then. What was the energy in? 138,450. And the specific latent heat, you have to be careful here, because look, that's kilojoules per kilogram. Okay, kilogram doesn't need to be changed because kilogram is the base unit, so it's 213,000. Put numbers in, and we get 0.65 kilograms. Leave your answer as that. It's fine. If you want to change it to 650 grams, that's fine as well. Okay. That's pretty much as we could be reasonably expected, and there's certainly no further than that. So here's a couple of extension questions, which are really more touching towards A level. Before we look at that, we've got extension question 6. I'm just going to explain. This is the experiment that we would do if we wanted to calculate the specific latent heat. So in this type of experiment here, what we're doing is actually we've got a load of ice here. And what happens is, clearly, even without a heat, what we do is we just watch, and if we leave ice in that funnel, what would we expect to come into the beaker? Well, we'd expect water. And that's because the ice is giving up its energy to the atmosphere, or the atmosphere is heating the ice. You could think of it that way. So both of those things are true. So the ice is being heated by the atmosphere, or the atmosphere is heating up the ice. Okay, let's have a look at this question. Measuring specific latent heat of fusion. So, what is going on here? Well, we can see ice in a funnel. And in effect, we can think of the heat energy from the atmosphere is actually, let's try and draw it in, is going in to, that's heat, isn't it? That's heat from the atmosphere going in to melt the ice. Or the other way, or we can think of the ice absorbing the heat from the atmosphere, and the ice is absorbing the heat from the atmosphere, and when it goes, if this ice is at 0 degrees C, then the energy is going to be going into breaking the bonds that make ice a solid and turning it into water. So the water's coming out down here, and the amount of water that comes out is really a measure of how much energy has been absorbed from the atmosphere. So in this particular question, what we do is we do the experiment twice, with more or less either just repetitively or with two identical beakers, one with a heater and one without. And if we leave it, what we can do, if you think about it, we had two setups like this. We had, let's clear the drawings on here. Maybe just reduce this down. And you can imagine if we had two setups here, and let's say we could magically, let's just draw on top of here. Let's see how this works. Yeah, I'll get the idea where I want to go. Let's just magically remove all of that. Okay, now If I've removed the heater from the ice, which one of these is going to melt more water? Well, hopefully you'll realise that the one that will melt more water will be the one with a heater in it. This will melt more water than the one below. We have two identical setups. Then actually what we can do is we can measure the difference in the amount of water that's generated, and the difference must have been supplied by the heater. So it's a bit of a complicated one really for GCSE. I'd put it in to give you a bit of a stretch, but let's go to it. Extension 6. In an experiment to find the specific latent heat of fusion, 0.24 kilograms of water was collected in a beaker in 300 seconds with the heater turned off. The beaker was emptied and placed under the funnel again. With the heater turned on for exactly 300 seconds again, so that same time, everything the same, the joule meter reading increased from 0 to 15,000 and 0.68 kilograms of water was collected in the beaker. So calculate the mass of ice melted because of the heater being turned on. Well, this is just the difference between the two, 0.68 and 0.24. That's how much mass was created between the two, 0.044 kilograms, 44 grams. So use the data to calculate the specific latent heat of fusion of the water. Well, for that we're going to use E equals ml. So L equals E over M. What was the energy that we put in to melt that extra water? Well, that was the energy from the heater, 15,000. What's the mass? 0.44. And that gives us a value of 304,909 joules per kilogram, or 341. Now, if you actually go to the question below, that's actually very close to the actual latent heat of fusion of water, which is 334. So this is an experiment. Clearly there's going to be extra heat losses, particularly there, or there might not be as much water collected, or we might underestimate. But in that experiment, that's a pretty good experimental value that relates well. So how long will it take a 50 watt heater to melt 2 kilograms of ice at 0 degrees C? Now here we've got the latent heat of fusion of water, 334 kilojoules per kilogram. So final question, E equals ml, 2 times 334,000, which gives us 668,000 joules. So now we've got the amount of energy. We've got the amount of energy here, but we also need to find time. So we need a formula that has energy. Here we've got power. So so we've got a 50 watt heater, which is 50 joules per second. How long will that take? Well, we say power equals energy over time. Time is energy divided by power. You rearrange that formula in a triangle. The energy, 668,000, divided by 50 watts. That's joules per second. So we divide joules by joules per second. We'll end up with seconds. Oh, that's quite a lot of seconds. 13360. Don't forget the S. If we want to divide that by 60, we'll end up with 223 minutes. And then we get down to, so quite a long time to heat that up. 3 hours, 43 minutes. Okay, that's the end of the lesson. Thanks very much. Bye.